Thanks for being with us in this webinar, in which we'll introduce 4 cutting-edge R&D projects related to wind farm control. My name is Marcos Suarez. I work for the Basque Energy Cluster in Spain, and I'm mostly taking care of the logistics today in the webinar. So just related to that, just two quick slides, and we can start with the presentations. First of all, some housekeeping rules. As you might have noticed already, we are recording the webinar, and we will share the recording with all of you and with all registered attendants together with the presentations after the webinar. We hope to do so in a week or so. Please keep your cameras and microphones off during the webinar. We will ask the speakers to switch on their cameras and microphones while they are presenting. In terms of the questions, there will be, in the original agenda, there was a Q&A at the end of the webinar, but we thought it was better to do the questions right after each presentation. So the way that will work during the webinar is that if you have a question for the speaker, please write it down in the chat. You can address it to me, to Marcos Suarez, Basque Energy Cluster. And then I will read these questions after each presentation, so that they are more connected to the presentation that was just done. If there are no questions, we will move to the next presentation. If we have too many questions, I will read 1 or 2, depending on the timing, and then we will try to reply all of them in writing when we share the recording and the presentations. Besides that, I won't go through the detail, but we have an easy agenda, let's say. We have first a welcome and introduction from Baris Adidoglu, who is the project officer of our project, the one we participate in WILLOW, and belongs to the European Climate Infrastructure and Environment Executive Agency. And then we have 15 minutes presentations for each of the 4 projects. And as I said, instead of 15 minutes at the end, we will have 2, 3, 4 minutes for each period of Q&A after each presentation. And please remember, if you want to make a question, write it down in the chat, address it to me, and I will read it after each presentation to the speaker. So without further ado, I give the floor to Baris. Baris, thanks a lot for being with us. The floor is yours.
Thank you very much, Marcos, for the introduction. I'll start by sharing my screen. And switching to presentation mode. Yeah, so hi everyone. My name is Baris Adidoglu, and I'm very happy to be here today. Thanks for inviting this nice seminar, and thanks for inviting me here. I work at CINEA, as Marcos said, and more specifically in Unit C2, which is Horizon Europe Energy. So my presentation today, the aim of my presentation today will be to set the background for later, for when the projects will present, so that the audience can put in context those presentations by understanding what the topic originally expected from these projects. So as such, I will start with a general information about the call. Then I will say a few words about Horizon Europe. And at the end, I'll be talking about the expected outcomes and the scope of the topic. So this call is part of Horizon Europe program. The projects were expected to be of research and innovation action type, which meant lower TRLs compared to other projects, for example, which would go on the demonstration phase. So it is an action grant budget type of grant agreement, and not, for example, a lump sum, which is also more and more the case these days. So, and it's a single stage model. The call opened on the 6th of December 2022 and remained open for a bit more than 4 months. So now a few words about Horizon Europe. As you know, Horizon Europe is one of the largest funding programs in the world supporting research and innovation, with a budget of 95.5 billion euros and extending between 2021 and 2027. So what we see on this slide is the main components of Horizon Europe. So these are, and their corresponding budgets in terms of billion euros. So the first one, pillar one, is excellent science. Pillar two is global challenges and European industrial competitiveness. Pillar three, innovative Europe. And the last one, which is not a pillar, but it is addressed as a part, is the widening participation and the strengthening of the European research area. This call that we are looking at today was under Pillar 2, Global Challenges and European Industrial Competitiveness, and more specifically under Cluster 5, which is one of the clusters under this pillar. So the Cluster 5 is the one also we look at CINEA. It is called Climate, Energy and Mobility, and it has a budget of 15 billion euros, again, from 21 to 27. And under this cluster, there are 6 different destinations. This call again was under destination 3, which is a sustainable, secure, and competitive energy supply. And under this destination, the areas covered are renewable energy, energy system grids and storage, carbon capture, utilization and storage, and cross-cutting activities. So now let's look at the topic. The topic had a total budget of 18 million euros. In total, 16 proposals were submitted with the initial idea of selecting 3 of them, but then a 4th one was also selected from the reserve list. And I think this also shows the importance that this topic has been given to at European Commission level. And here we see the projects which were selected, which are TWAIN, Iconic, WILLOW, and SUDOCO. So now let's look at what the topic expected from the proposals from the projects. The project results were expected to contribute to all of the following outcomes presented on this slide. So the main expectation of the topic was the development of an open source data-driven tool to decrease energy costs and at the same time of operation, and at the same time increasing total wind farm output, cost effectiveness, basically. Indeed, cost effectiveness and the open source nature of the tool were 2 important aspects of the call, which were treated as such during the evaluation. Of course, then the tools, the projects were supposed to also evaluate the operational risks arising from the chosen solution and consider operational security. So the tools could be either digital or physical. Interoperability was an important aspect. And here, once again, in the second one, we see the emphasis on improved performance at farm level. The projects were also expected to help the operators for making better decisions when it comes to farm-wide system optimization, lifetime extension, decommissioning, and or recycling of components. And finally, they were all expected to contribute to a reduction in a levelized cost of energy in line with the set plan targets. So here what we see is the scope. Basically, what the proposals were expected to include in order to convince the experts who made the selection and the European Commission that they would indeed do credibly contribute to the previously mentioned expected outcomes. So the first one is that the proposals were all expected to address how their innovation would be able to provide more stable, resilient, secure, reliable, and affordable energy while considering high levels of cybersecurity. So once again, wind farm output maximization is an important emphasis, and also an encouragement was also on the reduced component load. So another another thing that we wanted to see in the proposals were how these innovations would reduce operational and maintenance costs and increase energy output. And then they were also solution's impact on component, turbine, and farm lifetime. These tools were expected to be kind of prognostic tools, and as such, these proposals were expected to elaborate on their role in being so regarding failures and damages. So in the last one, we see once again the emphasis on the open source nature of these digital AI solutions for a sector uptake. And another very, very important aspect of this call was that the tools were expected to be built on concrete experiments and data measurements. And I know that this was a challenging aspect of the call, because I know that it's not easy to always find such data. But the European Commission really wanted such tools to have these concrete basis, and thus this requirement. So the tools were also expected to consider the future development, such that their tools would also be considered to eventually work for wind turbines up to 20 megawatts. And finally, as I said before, the expected TRL that the projects were supposed to reach was TRL 5, which meant technology validated in relevant environments. Well, this is all from my side. Thank you very much for your attention, for listening. Now I look forward to, as the rest of you, hearing what the projects have to present. And then the first one will be Iconic. So I leave the floor now to the Iconic project. Thank you.
Thank you, Paris. Good morning, everyone. I'm Xiao Zhao from University of Warwick. Today I will give an overview and the progress update of the Iconic project, which represents the smart, aware, integrated wind farm control interacting with digital twins. Iconic has 14 partners, including 7 academic partners and 7 industry partners across 7 countries. It started on 1st of December 2023 with a duration of 48 months. It has a budget around 5.9 million euros, funded by Horizon Europe and the UK government. Because the UK was not associated with Horizon Europe at the contract stage, the budget of the 3 UK partners, BP, Imperial College, and Warwick University, were funded by the UK government. For the same reason, I transferred the project coordinator to Professor Guillaume Carriou-Cara at Ghent University, and I became the scientific coordinator. So Guillaume and I co-lead the Iconic project. The overall ambition of Iconic is to develop an integrated wind farm control system to improve the whole wind farm's operation efficiency, thus leading towards more stable, resilient, secure, and reliable wind power. The Iconic control system is AI-based, data-powered, and physically informed, consisting of farm, turbine, and components levels. The integrated control system will be further supported by cutting-edge simulation tools and digital twins that are being developed within Iconic. To enhance this is to enhance the control performance. Iconic also explores the AI-powered lifetime management and cost reduction. Finally, a core feature of Iconic is a comprehensive validation by simulation, historical data, wind tunnel and test rig experiments, and real-world field tests. To deliver this ambition, Iconic has 4 objectives. Objective 1 is to improve the farm-wide operation by developing AI-based wind farm control tools. Objective 2 is deliver farm-level objective while developing turbine-level control solution. Objective 3 is to enhance the performance of the first two objectives by developing digital twins and physical tools as a control enhancer. And this enhancer will improve the awareness and control performance with the consideration of remaining useful life assessment of key turbine components. Objective 4 is to bring most of the innovation to TRL5 while comprehensive validation and tests, as mentioned earlier. As mentioned by Barris, TRL5 is a requirement of this call. Next, I will go through 7 main research highlights of Arconic. The first highlight is the AI-based control-oriented modeling of wind farm wicks. Safety models which can accurately capture the wind turbine wick interactions are computationally expensive, while on the other hand, the analytical models which can be evaluated in real time can capture the detailed flow features. In Arconic, we are developing AI-based wick models which can achieve simulation of high-fidelity flow features similarly as CFD models, while can be evaluated in real time similarly as analytical models. And the second highlight is the reinforcement learning-based farm-level control approach. In addition to what I mentioned earlier about the control system, we also consider strategy to reduce computational load and introduce a mechanism to enhance the cybersecurity. In recent years, we have focused on developing intelligent wind farm control methods that are trained, tested, and refined via simulators. This allows our reinforcement learning strategy to learn and improve in an environment that mimics real-world conditions. In Arconic, we are also exploring a new, more data-driven approach in which we use historical data, or called offline data, to train our controllers. This method could potentially reduce the need for interactions with wind farm simulators or physical systems. Additionally, by using offline data, we can possibly incorporate the experience of the engineer in the control room. So we include the humans' experience in the training of our reinforcement learning-based controllers. So we call our strategy offline reinforcement learning-based wind farm control. We use the C-Powers wind farm layout as a simulation test case to test the performance of our offline reinforcement learning controller, which is marked in red in the bar chart. It achieved a 16% increase in the power captures compared to the grid case. It also outperforms two other non-AI control methods. The third highlight is a turbine level control approach. We developed novel MPC approaches to enhance the control performance and ensure strict safety requirement. All these proposed MPC methods for wind turbine control will benefit from pattern Ampletek's Forces Pro suite, which is a commercial product for deploying MPC and numerical optimization in wind turbines. So this work is ongoing, and we are going to report the result in due course. The fourth highlight is the farm-level digital twin, which will be developed by physically informed deep learning approach. The digital twin can reconstruct the whole flow field in the entire wind farm. This will be achieved by fusing various data and physics simultaneously into the physics-informed neural network structure. By physics and data fusion, the digital twin will provide wind flow field information that cannot be directly measured by current sensor technologies nor predicted by conventional machine learning approaches. A recent progress that we achieved is a reconstruction of the in situ spatial temporal wind turbine wake flow fields, as shown in the right videos. The top video shows the digital twin. The bottom video shows the ground truth. It is shown that the whole dynamic flow fields are successfully reconstructed based on measurement only at a sparse location. The captured features, including both the flow structure propagation in the wind direction and the wake meandering in the crosswind direction. The next step is to extend this to three-dimensional case and explore the way to use such rich flow field information for supporting wind farm control system. The fifth highlight is the turbine level digital twin, including key turbine components. This including drivetrain, the generator, the main pitch, and yaw bearings. High fidelity models of these critical components are being developed and calibrated with historical data. Once this is done, surrogate model will be built based on high fidelity models to achieve real-time performance. The surrogate models will be deployed based on either data-based machine learning approach or hybrid approaches. This will depend on the component characteristics. These surrogate models will be integrated all together to form the digital replica of the physical system. Such digital twin system, along with the online sensor measurement, will then be used to support the control and management, considering the remaining useful life of the key turbine components. The sixth highlight is the extension and adaptation of the developed control and digital innovation towards future 20 megawatts wind turbines. We will also develop a repowering strategy using 20 megawatts wind turbine for C-Power's wind farm to demonstrate the use of the tools developed within the Arconic for repowering and decommissioning scenarios. The final highlight is comprehensive validations. As mentioned earlier, this including validation by simulations, historical data, test rig, wind tunnel experiments, and field tests. At wind farm level, numerical tests will be carried out while large eddy simulation of atmospheric boundary layers and wind farms based on 3 case studies, which cover an onshore case according to one of the BP's onshore wind farms, an offshore case according to C-Power's offshore wind farm, and a future wind farm case consisting of 20 megawatts wind turbine design. All these 3 case studies will be used for evaluation of the digital twin and the control system within the simulation environment. It will ensure that the Arconic innovations are generic to wind farm and turbine specifications, therefore maximizing Arconic's potential impact. Then validation by physical experiments will take place in the wind tunnel at Imperial College. Extensive turbine array experiments in realistic atmospheric simulation will be carried out. where spatially extended high resolution measurement will be achieved by a combination of the PIV and the point velocity measurement. So Imperial is currently setting up this experiment. At the components level, the test bench for critical components will be used, available at Lolagen. Finally, the field tests will be carried out at Seapower's wind farm. With all these tests, we expect that the iconic innovations will be well validated, and the major innovations will reach TRL5 at the end of the project. So this is the project overview and the update from me. Thank you very much for your attention.
Thanks a lot, Professor Zhao, for the presentation of Iconic on time. We have no questions. I remember everybody that if you have any question during the presentation, you can write it down in the chat. But then we move to the next project. In this case, it will be SUDOCO, presented by Professor Van Wingerden from the Technical University of Delft. Jan, are you there? Jan Willem? Well, I guess there might be some technical issue with Jan. We can move to the third one, and we'll try to reach Jan Willem during the presentation. So we'll move to the next presentation of TWAIN. In this case, it's introduced by Tuffe Guzman from DTU Wind and Energy. Hi, Tuffe, the floor is yours. Thanks for being quick to react.
Hi, everybody. No problem. I hope you can see the screen all nice and clear. Let me see. Probably you also see yourselves a little there. Okay, good. All right, so let's talk about TWAIN as a second one today. So TWAIN is integrated value-based multi-objective wind farm control powered by AI, obviously funded under the same call with all the 3 sister projects. So T within TWAIN is coming from towards, but we thought it wouldn't be as ambitious. So we said instead of going towards, we will go completely at it to the bullseye and complete our work at the TRL5 as much as possible within the 4 year of the project. We have started November last year, and we have a little bit more than 3 years to go now. These are our partners. So in TWAIN, we have quite a heavy representation of the industry. There's 4 research institutes, as you can see. There's us, DTU as the coordinator. There's CINEA from Spain. There's TU Munich from Germany. And there's also TU Delft from the Netherlands. And from industry, we have 3.5 owner-operators coming in. And that will be EDF and Vattenfall. And Engie is coming with 2 of their entities. So that is Engie Green from France and Engie Laborelec, they're more R&D leg in Belgium. We also have Ramboll coming in with 2 entities. So that will be Ramboll Denmark and Ramboll Germany. So these are potentially the partners that we are sort of used to see in wind farm control related projects or any kind of wind related projects. But then on top of that, there is a partner of ours that we think is a step towards more AI application, and that is SoftServe. They are the software engineers coming to the consortium from Poland. And then we also have S6S, who are in charge of communication, dissemination, exploitation work package, and also help us arrange or be here today in this workshop. All right, so TWAIN narrative, as you can see from our figure on the left-hand side, is taking the business as usual. And first of all, try to model how we can digitalize those processes that is relevant for wind farm operation around the wind farms. We are focusing on both onshore, particularly heavily on onshore, and a little bit of offshore. And we are very much interested in digitalizing the processes, but also the value. So how much of the value we can create by controlling our turbines. So in that regard, we are also looking at the social aspects that is a little different, perhaps, with our sister projects in the same call. Over here, we're asking questions particularly related to noise, related to sound, the acoustic part of things, how we can actually digitalize, model the processes regarding the emission of the noise, propagation of the noise, and perhaps a bit more social side of it, how the noise is perceived by our neighbors, by our social environment around the wind farm, and how we can mitigate those effects. We're also looking at wildlife. So we are aware that there are a lot of birds and bats and a lot of wildlife that is also affecting the wind farm operation, how those effects can be modeled, and how they're actually impacting the rest of the workflow when it comes to modeling the performance, when it comes to optimizing the performance. And then we're also looking at precipitation and rain. We know one of the most expensive unscheduled maintenance around the wind turbines is happening due to leading edge erosion. It's driven by rain, especially in Northern Europe, but also hail and different precipitation factors in the weather. How we can actually take that into account together with other projects that is funded under EU, and how we can take that into account to calculate our O&M costs so that we can set up a more realistic revenue stream for our digital twins. So just like any European projects, we also have some work packages, which we also call pillars, because they are highly associated, highly correlated with our objectives. So our very first pillar, or let's say the foundation of TWAIN, is basically on the data environment. So that is about integration of multi-source and multi-format data, how we can integrate them, how we can actually ensure that they're safe in 3 different levels, which I will talk a little bit more in detail later. And this is our very first work package, and this is also where we started from the project. And then in our work package 2, we're taking all this data, we're looking at all this measurement sensors information that we have regarding the state of the wind farm and its operation, and then we start modeling the processes that are relevant for us. Some of them are very traditional processes, like the wind farm response itself. That would be the power, structural loads. We also look at failure and damage effects, but we're also looking at grid compliance and services. And as mentioned, we're looking at some eco-social consciousness aspects. Then our third work package, which is at the heart of TWAIN, is actually about the value. So how we can turn those processes, use them as performance metrics, indexes, defining the risk and uncertainties, how we can come up with societal metrics on top of the economic metrics to define more sort of rounded value for the future regarding the wind farm operation. And our fourth work package, which is sitting on top of pretty much everything else technically, is about integration of the multi-level controller. So how we make sure there's smooth communication between the turbines within the wind farm, how they communicate with the central farm controller, and how this farm is actually communicating with this wider environment around. And then our last work package is integration of you guys, so wider audience to the TWAIN outcomes. And for this, there is one particular aspect which I think you will find interesting, and that is the open call, which I will also talk about in a second. So within TWAIN, it's a little crowded slide, I'm aware, but I hope you can follow with me, especially if you can see my cursor, it's going to be easier. So TWAIN is for its end users, which are the owner operators of wind farms. They're coming with their data, that is social environmental data and O&M data. They're coming into our what we call data environment. And the data environment is secure, it has AI machine learning capabilities, and then we start modeling some of the processes relevant for that particular wind farm. Some of these are very site specific. And then, for example, some power, loads, damage, noise, wildlife aspects, they're feeding into work package 3, which is a socioeconomic and environmental impact assessment. And from processes, they become actually value. So power becomes AEP, or it becomes income. Loads, structural loads, particularly, they are going to be converted into O&M costs and lifetime, etc. So all those metrics, and noise become constraints, for example. So all those metrics, objectives and constraints, problem formulation for optimization is happening over here. And then we put them into the control integration and the optimization so that we can have this decision support. So we have this series of optimum decisions for humans to choose. And of course, together with some field validation over there. And then we're opening version 0 of our environment. About 2 years from now, we will actually have an open call, meaning we will be actually having, let's say, another call within our project, which is also funded by a call, where we will be looking for 3 collaborators with us who are willing to be the guinea pigs, if you will, of the first TWAIN environment that has all these aspects, and they can actually help us with their user experiences so that we can use that to release our final version by the end of the project. As I said, we're going to be funding 3 projects, and they will also granted about 25,000 euros each. all the processes of it, and the entire progress is run by our partners, F6S, and we will, please follow us. You will definitely hear about that more about 2 years from now. Let's look at our case study. So what is TWAIN going to investigate a bit more specifically? So the first one is about environmental and social ramifications, which is very important for us. So here we have already defined 2 separate test cases. We will be looking at some NG wind farms in France, where the noise itself or the noise emission itself is quite problematic. So the wind farm is experiencing a lot of noise curtailment. So we're going to be investigating, for example, is there any other way that we can do smarter control for the noise instead of old school, let's say, curtailment? Can we actually reduce the noise by misaligning the turbines so that it can help with wake steering? So maybe not losing power or even increasing the power. Can we keep the noise within the constraint limits? We also have quite a bit of interest when it comes to particularly bat observations within France. So we are going to be looking into how we can do the controls in regards to wildlife and the caution regarding wildlife. Can we do it more smart? Our second case study is, because majority of our tools will be based particularly on the onshore case studies, we will test how they are adaptable to offshore. And for that, we will use a very well-known wind farm for the community here. That will be the Lidgrund wind farm. We will be looking into the data set that is collected during the total control days. Some of you might remember Horizon 2020 project. And we will see how our models perform offshore. Our third case study is looking into the future. So that is considering large turbines, 20+ megawatt turbines. Currently, we're planning to use Rumble prototype for this. And then over there, perhaps more interestingly, we will be looking into, let's say, some simulation, some prognosis regarding the future, both in terms of market, how the markets are going to be 2050 and onwards, especially including climate change effects. And our last case study is looking to of life decisions. So given the site, given the conditions around the site, is it a better idea based on several different metrics, not just economics ideally? Is it a better idea to go for repowering? So demolish the existing wind farm, put up newer ones, ideally bigger turbines, or is it a better idea to for lifetime extension using the control capabilities we have? We also have field tests planned, so they will also start about 2 years from now or 1.5 years from now. And this is using our brand new facility in Research Campus. Maybe some of you have seen that in LinkedIn. We also have the second turbine built up now, which is closer to the road if you ever visit 3T. So we will also perform some tests, particularly focusing on the power maximization with the load constraints. We will be testing some of those, and we will also see the differences, how it affects power maximization versus income maximization with variable market scenarios. So our progress so far is mainly about the work package 1, which was the data environment, as I said. So over there, our objective was to design a framework to integrate all these different data sources. And of course, it's very important that we ensure the data integrity and we come up with certain standards, because every wind farm, they have different ages, they have different kind of data logs, they even have different taxonomy and ontology for their data. So uniform them is one of our main goals. So this framework, the entire TWAIN environment is going to be open source. And we also want, of course, all of this to be interoperable. So if you want to use just part of the TWAIN environment, you should be able to do that, integrating with the rest of your, let's say, in-house workflow if you're one of the end users. And of course, we want the cybersecurity to be highlighted for all the environments, and we believe the secure by design is the way to do that. So currently, the architecture vision development has been finished, and also technological setup and the deployment is completed. So this is pretty much what it looks like. It's a little bit of a busy figure. So one of the things I can already say is that the entire framework, for the people who are not familiar with the software systems in general, the key clock will be our entry. So this is going to be where the authentication authorization will work. And as users, which I find particularly interesting, is that you will have a Jupyter notebook on your own running at our DTU service that you can actually interact with the rest of the environment. So you can come with your own data. Ideally, you're coming with your own data, and then you're sort of reading, coupling the models and metrics we're developing within TWAIN, and you start your analysis from there with your interaction through notebook particularly. But as a user, you also have the freedom, since it's open source, you also have the freedom to look at individual components separately. So you can choose to use just min.io or Trino. You can also use open metadata, etc. So our security layers is basically three layers. So it's the application layer, software, or solution layer, and then we also have the data layer security. In order to get there, we have had several quality attributes workshops. We have lots of partner questionnaires to define what the user needs would be, since we have 3.5 owner operators on board. And then we have gone back and forth iteratively to come up with a final design that you see here. So we are currently implementing it in the DTU servers. Now it is open only to the consortium, but we're hoping for public access very soon. As I mentioned, there's 3 levels of security. For all the levels, we are authenticating and authorizing users. So you come with your own login through key clock systems, and based on, for example, your company email, you can actually have access to particular data versus you are restricted to look at other data, which is also very important for us in this competitive business. And that's partially the work of the data management. On top of that, we are also looking at the data standardization methodology. So whichever your data set have the ontology for, we have currently mapped particularly 4 different turbines and come up with the IEC, so conversion of their ontology to the IEC standards. And this is what we're introducing to the rest of the workflow. So the very first step the data environment does for you is to use the ontology and convert or use the standards to convert your data set so that the workflow can actually read it long term. And that's an automated environment. As I said, it will be open for public access pretty soon. So please follow us on TWAIN Project on LinkedIn, or look at our website, subscribe to the newsletter. That's also twainproject.eu, so that you can also hear more about the development of the environment itself, both for the data and also for the models going forward. So thanks a lot.
Thanks, Tufe. I have 2 questions for you. First, Alvaro Blasco asked why the turbines Vestas V27, because their size is no longer commercial.
That is true. That was also a lot of internal discussion within DTU, as you can imagine. So one of the limitations is that our fjord is a protected area, so we anyway have quite a bit of constraints on the total height we can have for the turbine. Second of all is the overall space that we have. So you might be aware we won at a wind farm, meaning we needed 2 turbines, and we already had 1 V27 and 1 V52. Buying another V52 would also be feasible, but then they had to sit very close that it wouldn't be realistic to do weight studies on it, because we don't have too much space laterally. So we had to go for the V27 option. And even with that, we are a little bit too close to the road.
Okay, thanks. And the other question is from Jacob Berner. His question is on a case study regarding noise impacts. He asks, do you also look at acoustic properties that are not covered by national noise regulations? In example, he says that one of their findings in this area was the communication of forecasted noise emissions can lead to reduced perceived annoyance. I know what to expect, so I am fine with the nose. Yeah.
Oh, that is a very, very good point. So yes, legislations are not necessarily based on perception, and they're not necessarily taking the social environment into account at all. They are very much technical in that sense. They are based on decibels and very regulated by the IEC methods of doing that, etc. I would be very interested if you have further information about that, particularly the perception, particularly anything that can give us the classification of annoyance versus the actual, let's say, emission plus propagation. I would be very interested in sharing that with the rest of the team.
Okay, we can put you both in contact after the webinar then.
That would be great. Thanks.
If that's okay with Jacob also.
Yeah, hopefully.
Thank you. Then
Thank you.
that's all. Thanks Tufe for the presentation. Thanks for the questions. We come back now to Jan Willem van Wingerden. Jan, are you there now? There you are.
I am. First of all, my apologies. I was disconnected somehow from my docking station.
No problem at all.
I will share my screen. Share screen. Yes.
We see the screen now?
Yes. Oh, 1 second, because things now changed.
Presentation.
Beginning, I have to change this one to this one. So now
There you go.
see my screen, right?
Yeah, perfect.
Good. So yeah, so welcome everyone. My name is Jan-Willem van Wingeren. I'm a full professor at the Delft University of Technology in the field of control systems, leading the data-driven control group. Typically working on wind farm and turbine control. So I mean, this project is in the core of the work that we're doing here in Delft. So the SUDOCO project stands for Sustainable, Resilient, Data-Enabled Offshore Wind Farm Control and Co-Design. So the data-driven, we have seen that also in the call. A wind farm control, clear. The co-design is something we added in this particular project. So what I will do is I will try to give you the feeling of the SUDOCO project. And the first thing I would like to show is to give you this overview. Because how we see the SUDOCO project is that we build upon previous EU projects and national projects. So there has been a lot of work done in the field of wind farm control, but mainly they're working on a single technology like wake steering, induction control, dynamic induction control, and you name it. So as you see here, right, there are different concepts on how you can manipulate the flow within wind farms. Wake steering is the most common one used, and it's about steering the wake to make sure that downstream turbines produce more energy. But there are also new ones like dynamic induction control and really old ones like induction control. Most of these techniques are developed for steady conditions. Steady conditions meaning a given wind direction, given atmospheric conditions. So in this project, we would like to mature this technology by looking into time-varying environmental conditions. So also taking into care the day and night, fear, shear, all these type of things, and also focus on large wind farms. I mean, previous studies were typically small wind farms. Objective is typically to look into just maximize the energy capture of these wind farms, but you have to also take into account the energy market. So you also see it here at the left, so the time varying market conditions. I have an illustration later on, because the price per kilowatt hour is not the same for each wind speed. So time varying input conditions, and then we have different flow control technologies. And then you also have to look at the effect of flow control. So you can produce energy, but you also have to realize that these machines, these wind turbines, have to be out there for at least 20 years. And there's always a trade-off being too aggressive to create a lot of energy out of the wind, and also the loading on the individual turbine. So you can imagine that at some point you want to say, hey, the prices are really low, so we have to save the lifetime of our turbine. So you prefer then to minimize loads instead of going for a high yield. Now, these are as an example of playing with these control settings. Now, then you also have to look into the objective function. So a typical objective function, what I already stated, was let's try to maximize the energy production, but there's much more. So also in this project, we're also going to look into different objective functions. To name one is the cost of valued energy, which you can see here at the right-hand side. Of course, taking health into account, and also at the end, what we would like to do is take care of the safety of our turbines, right? So safety means loads, but also we have to protect our assets for cyber attacks. So that's also an important part of this project. So we put everything together in an open source platform tool. And at some point, we also would like to introduce storage, solar, etc., to really have a platform for wind farm operation. So what we would like to end up with at the end of the project is the control room of the future for offshore wind farms. So that's maximizing a certain objective function and developing an open source data-driven platform that will find a trade-off, for example, between maximizing the energy production and mitigating structural loads, but also other objectives can be added. So that's something we're going to explore. I will come back to that when I introduce the different work packages. So everything will be integrated in the control room of the future. And we will test the control room of the future on experimental data, field experiments, and also wind tunnel experiments, and also integrate cybersecurity measures. So at the end, it's integrating a lot of existing technologies and also combining them. So that's also where the name is coming from, the SUDOCO, and you probably know the puzzle. So at the end, the SUDOCO project is basically solving a puzzle, and that's what we're currently trying to do. So in the start of the project, thanks to Icons, we already have a really nice movie that will introduce again the concept of the SUDOCO project. So let me try to play this movie. Hopefully there's not too much delay, and otherwise we will share the link on how it's called YouTube.
In his epic journey back home, the legend says Odysseus encountered the god Aeolus, who can find all his winds within a mystical bag, saving just the one destined to guide the hero home. Thinking it contained a marvelous treasure, Odysseus' companions opened the bag and released the winds, sparking an uncontrollable storm that has lasted until now. However, modern science, data, and algorithms can finally help us harness the immense power of the wind, which is set to be the key asset for Europe's journey towards carbon neutrality. This is where the SUDOCO project blows in. With its control room of the future, SUDOCO is set to introduce an innovative open-source data-driven platform designed to achieve an optimal equilibrium between maximizing energy output and mitigating structural stress, especially in offshore wind farms. The SUDOCO project has 4 main goals. 1. Implement flow control for wind turbines, reducing costs by as much as 10%. 2. Develop a control system for a 10% reduction in the cost of valued energy metric. 3. Optimize the entire wind farm system to decrease lifetime CO2 equivalent emissions by 20%. 4. Enhance cybersecurity to ensure an uninterrupted energy supply. Follow the flow of the SUDOCO project and its control room of the future. Discover how it can help solve this great puzzle for a greener and more sustainable Europe.
So it's a puzzle, right? It's a puzzle, and what I didn't mention that the focus of this project is on offshore wind farms. So we have these different work packages, different focus. So the first one is flow control. So I already indicated that flow control was part of many European projects where they focused on wake steering, induction control, and all these things. What we will do in this project is we are going to integrate the different technologies, because some of these technologies work very well for certain wind directions and wind speeds, and others work better for another configuration. So the focus here is to integrate different wind farm control techniques. And on top of that, to make sure that we can really implement them in the field, so look at scalability and reliability of these control methods. So the focus here, large wind farms, maturing flow control technologies. Now, if you have the flow control technology, then you also have to look at the impact, because if you do flow control, there is also an impact on the structural loading of your turbine. So what we have to do is really understand the impact of wind farm flow control on the loads and the health of these machines. So what we will do is we'll build load surrogate models such that we can also add loads to our objective function when we want to optimize the performance of our wind farm control solution. So that also brings me to the next one, and that's the value function. So the value function at the end is what you want to optimize. And what we will do in this project is we will explore different value functions. So this can be an economic one, but can also be an environmental one, and these type of things. For example, if you look at the picture at the right, you see that the spot market price of electricity is higher at low wind speeds than at high wind speeds. So you can imagine that you want to make a trade-off here between lifetime and how aggressive your controller will be. So then we have flow control, we have load modeling, we have an objective function, and everything will come together in the control room of the future. So this is our open source platform, software platform, where we integrate these different control technologies with a strong focus on cybersecurity. And of course, the data-driven aspect of all the methods that we develop. Now, the control room of the future is the center of this project, which we will use in the co-design approach. So co-design means that if we have our flow control algorithms, can we, for instance, also optimize the turbine and or layout of the wind farm. So that's what we will do in work package 5. And here at the right, you see a Pareto curve. Again, a trade-off between, for example, yield and loss. And what we believe is that if you do co-design, then probably you can move the Pareto curve further to the bottom left, to point D in this animation. Now, as an example, as one of the first results where already a couple of things come together, is that suppose that you do conventional wake steering and you look at the layout of your wind farm, can you then increase the annual energy production? So still a conventional objective function. And the answer is yes. I mean, you see in this picture at the right, power density versus AEP improvement. And forget the details, but what you see is that these lines are going up. So there is a potential improvement of 0.2%, which is significant. The lines that go down say, hey, if you optimize for extra energy and you don't switch on your turbine farm controller, then you lose power. So that's also what you see in the same figure. Currently, we are a step further and again exploring the Pareto curve, if you can basically find a trade-off between losing power and increasing the AEP gain. Finally, we also are going to demonstration like all the other projects. So we will get data from a large offshore wind farm in the North Sea. We will also demonstrate the control room of the future within the wind tunnel in Milan. So here you see a screenshot at the right of the wind tunnel. And there we are going to demonstrate the control room of the future under realistic time varying conditions. And again, finding a trade-off between all these different flow control technologies. So if you now look at the whole project, then you see all the different work packages. So I talked briefly about work package 1, 2, 3, 4, 5, and 6. But of course, we also have a dissemination exploitation work package and a project management. What I would like to mention here is that we really build upon the shoulders of others, right? We build upon previous EU projects like CO WindCon, FarmCon, Total Control, and also ongoing European projects. And what you also see in this overview is the partners involved. So we have academic partners like TUM, DTU, Politecnico di Milano, but we also have industry like U-Wind Renewables that are developing the control room of the future, Sovento, an expert in floating wind, and also Shell responsible for the demonstration. Besides that, we also have an advisory board containing NWEL applied risk for the cybersecurity, Siemens, so that should be Siemens Gamesa, Crosswind, the owner of the offshore wind farm in the North Sea, and Widesco, a company in the US working on wind farm control solutions. So again, these are the partners. I already mentioned that. What I would like to highlight is that we have our nice SUDOCO website, also with the movie I just presented, and please also look at our LinkedIn account. So thank you all for your attention.
Thanks a lot, Jan-Willem, for the presentation. We don't have questions in this case, so thanks. We move to the last presentation of the day. In this case, it will be Ainhoa Cortés from the Technology Center CEIT, who will be introducing the project WILLOW. Ainhoa, the floor is yours.
Hi, good morning, everybody. Let me first share my presentation. Okay. Okay, I hope that you can see my screen.
It is, yeah.
So, okay, thank you. I'm Ainhoa Cortés from CEIT, which is a research institute in the Basque Country in the north of Spain. And I'm the WILLOW coordinator. And it's my pleasure to be here today presenting the project, which is for holistic and integrated digital tools for extended lifetime and profitability of offshore wind farms. So let's go. Some general information about the project, the call and the topic, which was explained by Baris. The budget was around 6 million euros, and the project started last year in October, and it's a 3 years project, so will be finished by September 2026. Okay, this is the consortium in WILLOW. We are 12 partners from 5 different countries, where we have 4 research institutes, where CEIT is the coordinator, 1 university from Belgium, 1 offshore operator, who is Northern from Belgium as well, and 5 small medium enterprises. So let's say that we have a very good industrial representation on board, and 1 cluster, which is the Basque Energy Cluster. As you know, Marcos is there. Okay, so this is the outline of my presentation, starting with presenting the context and challenges, then the objectives of the project. Then I will talk about the work packages and the activities ongoing. I will show you the advisory board we have formed in WILLOW, and finally the outcomes and the expected impacts of the project. Okay, let me start putting in context the motivation of this project. Nowadays, the operation of offshore wind farms is not ideal, because we must handle with fluctuating conditions of wind availability and power grid demand. And on top of that, in offshore, we have very harsh environmental conditions, which affect negatively the structural health of wind turbines, and consequently the useful lifetime of these structures. Then the excessive non-regulation and frequent start-stop events affect the fatigue life of the wind farm structures. Let's say that the turbines can operate sometimes in off-design conditions. Then how is it done today? Today, different strategies are applied, like stopping a few turbines and letting the others produce maximum power, or down-regulating its turbine by the same amount of energy. These kind of strategies, let's say that have negative effects in fatigue life of the wind farm structures. Then here we have a challenge. This is our problematic, that there is a lack of success in implementing new decision-making schemes. And why is this happening? Because the component degradation and grid integration is particularly complex in offshore. And on top of that, we have additional degradation rates. For example, if we talk about corrosion due to moisture and salinity, or we have additional loads due to waves, tides, and currents. That's why we propose the WILLOW approach, which is some kind different from the other projects. Here we propose an integrated system to provide an open source and data-driven smart curtailment solution. Let's say that we are focused on this curtailment situation, and taking into account the degradation of the wind farm structures. We look for a trade-off between power production and lifetime consumption. To do this, we defined 3 technical specific objectives. The first one is the design of a global structural health monitoring system based on different physical parameters like loads, accelerations, images, thickness losses, etc., and taking into account problems like fatigue, pitting corrosion, and coating degradation. And the idea is to use or to develop physical and virtual sensors combined with machine learning techniques. The second objective is more focused on the design of prognosis tools, combining SCADA and structural health monitoring data coming from our own system or coming from other deployed sensors, and using physical models and machine learning methods to predict the consumed lifetime and the remaining useful life of the most critical structures of the wind turbine. And the third objective is to design the decision-making support tool for smart power dispatch in curtailed conditions. As I said, we are focused on that situation, and also to optimize the operational maintenance scheduling of the wind farm. Okay, this figure shows the interaction of the 4 technical work packages. Of course, we have the 2 other work packages for power management, project management and dissemination and exploitation. But here you can see the 4 technical ones. Then work package 1 is focused on the definition of the use cases. We can say that we finished with this definition. Our main use case is focused on the northern offshore wind farm and in the curtailment problem. And here we will use other offshore test environments like Blue Accelerator and HasLab to get more data for our modelings, and also to validate the sensors or the physical developments of this project to validate the robustness of the system and to verify if everything works fine in a real environment. Then currently in this work package, we are working on the definition of cybersecurity strategies at wind farm level, considering also the cybersecurity issues in the monitoring solutions. And also we are working on the development of a system to measure the noise pollution of this offshore wind farm. Work package 2 is more focused on the design of this novel structural health monitoring system combined with drone-based inspections. that's why we have drawn company in these work packets. Then here, the solution we are developing, as I said, try to solve the pitting corrosion problem and measuring the coating condition continuously, and also consider the load damages of the structures. Then we made, during this time, some progress in different technologies like ultrasounds, thermography, electrochemical sensors, also accelerometers and virtual sensing, to combine the different techniques and analyze in depth the limitations of each one, and try to detect in the best way the different pitting situations and degradations in the coating. Then we have developed some experiments in lab with the different techniques, and correlating some of them. And we are developing also some modeling, because the aim is to detect the problem and also to be able to quantify with a good precision, and also try to predict that this will happen in the future. And if we go to work package 3 and work package 4, this work packages work at wind farm level. Let's say that work package 3 has not started officially, but we made some work in the development of the platform for the structural health monitoring data collection, the data coming from work package 2. And some work also in the fleet life load modeling. And in work package 4, more focus in the design of this open source decision-making support tool and wind farm control. We are defining the future grid scenarios and analyzing the effect of curtailment on damage equivalent loads. And the most important thing is that these work packages, work package 3 and work package 4, are working together, because in this project it's important to consider the fleet life assessment in the wind farm control strategy. Okay, as I said, Northern is our offshore operator, which is on board. Then, WILLOW project is focused on this use case in the Belgian North Sea offshore wind farm operated by Northern with 44 wind turbines. Then the developments in work package 2, 3, and 4 are receiving data for the use case to be able to develop modeling with real data. And for Northern and other operators, the curtailment situation is important. And here, the aim of WILLOW is to analyze in depth this curtailment situation and how the high fatigue loads suffering from this situation can be in some way detected and predicted, and to take some mitigation action and to do the control accordingly. And these offshore test sites will be used as well, the Blue Accelerator in Belgium and the HASLab in the Basque Country, to perform some experiments with some of our sensors. As I said, we are working with different technologies in that sense. Yeah, we have here two different objectives. The first one is to get even more data for our machine learning methods developed for the different techniques or problems I mentioned. And on the other hand, to validate the robustness of the solutions developed in WILLOW, and to confirm that that the solutions can work in these real environments, offshore environments. Okay, this slide shows you the advisory board or the participants we have in the advisory board of WILLOW. We can say that this is a very strong advisory board with a good, important companies in the field we are working on in WILLOW. And we will have the first meeting with them in November, at the end of November in Belgium. And we divided in different subgroups related to the topics we are working on in WILLOW. And we received a very good response and a lot of interest from these participants. So yeah, we are looking forward to hearing from their feedback based on the huge industrial experience of them. And just a summary of the outcomes we foresee in this project. As Baris presented in the call, this is aligned with the topic. Then the first one is the design of open source data-driven tools. The second one, the development of digital and physical tools, and we will do that, of course, to enhance the data collection, analysis, and operation, to be able the operators to make better informed decisions on different things like farm-wide system optimization, lifetime extension, and decommissioning. And the fourth one is all of these projects has this target, which is the reduction of the LCOE. And of course, the expected impacts WILLOW will impact in different things like maintenance cost, design and operating life, environmental impact, levelize the LCOE. And some numbers of these impacts, for example, we aim to reduce the inspection cost in 50%, or to achieve to increase the lifetime extension, with 5 additional years of operating life of the structures, to reduce the noise pollution by 4%, and the reduction of LCOE up to 10%. And this is all from my side. Thank you very much for your attention, and it was my pleasure to answer your questions. Thank you.
Thanks, Ainhoa. One quick question to finish the webinar from Irache Menchaca. She asked if, apart from corrosion, are you considering biofouling in the material degradation increase?
Okay, this is a good question. We are working more not in the submerged area, more not undersea. Okay, then one of the areas we see that are most critical is the transition piece. And here the pitting corrosion is more important, and we are trying to, of course, in the consortium, some partner is producing samples with pitting. Okay, then the idea is, or we are measuring those samples in the lab, and of course, we will do this, or we will continue with the experiment in the HARS lab and the Blue Accelerator to see how these pits evolves. Okay. So, well, via following is not, in principle, is not considering in the project.
Okay. Thanks, Ainhoa. Thanks for the presentation. And with this last project presentation, we finished the webinar. Thanks all attendants and all speakers for participating today. As you see, all these 4 projects are starting. So we encourage you to follow those who are of more interest to you in the websites, with the open calls, with advisory boards, any way you prefer to interact. So thanks again to everybody, and have a nice day. Thank you.